Welcome everyone to today's webinar from the European Nuclear Society about the circular economy of nuclear, turning challenges into opportunities. Very nice to see that so many of you are able to attend this webinar. My name is Veronique Vasseur and I'm your moderator for today. I work at the Central Organization for Radioactive Waste in the Netherlands, and I am the Policy and Strategy Advisor there. Besides that, I'm the president of the Dutch Young Generation. Nowadays, the circular economy and sustainability are a top priority, and therefore it is very important to also look at the opportunities for circular economy in nuclear. Today's speakers, DJ Leonard and Sven Bodem from the Belgium Nuclear Research Center, SCK CEN, will learn us more about the challenges that are faced in this field and how we can turn those possibilities to make those nuclear sector more sustainable. Before I proceed to our first speaker, I would like to inform you that questions can be asked after both presentations have been given. If you have any questions, please write them down in the chat. So our first speaker will be Didier Leonard. He is a nuclear engineer with over 20 years of experience in the nuclear sector. He has worked on the maintenance of nuclear power plants in Belgium for ENGIE Group for more than 10 years. He then joined Ondrof Nairas, the Belgian waste management organization, for more than 8 years. He was responsible for the design of the geological disposal for high-level waste and also for the cost assessment of the waste management in Belgium. He moved in 2024 to the Belgium Nuclear Research Center, SCK CEN, where he became director of the Institute Sustainable Waste Management and Decommissioning. The institute is implementing the SCK CEN strategy for circular economy. Today, he will learn us more about SCK CEN and the RECUMO project that is currently running over there. So please, DJ, go ahead.
So thank you, Veronique, for the nice introduction. First of all, good afternoon, everyone. It's quite a pleasure to go a little bit deeper in what we are doing at SCK CEN concerning the circular economy. I will just go to the next slide. So the agenda of today, as mentioned, there will be three main parts. The first part will be dedicated to SCK CEN, just to introduce what is doing the Belgian Nuclear Research Center in Belgium and how is the circular economy integrated in SCK CEN. Then the next point will be the presentation around the project RECUMO. So I will do this presentation. It's about recycling of nuclear targets used for the production of medical radioisotopes. And the last presentation will be done by my colleague Sven Bodem concerning the management of radioactive waste in Belgium in a sustainable way, and especially the role of the clearance which are in the Belgian law. So first of all, let's start with SCK CEN. So as mentioned, SCK CEN is the Belgian Nuclear Research Center. It has started its activities in the years 1952. The main objective of our research center is to deploy innovation around the nuclear fields in different domains in order to bring the innovation to our partners or customers, but also, in more generally speaking, to the community. Concerning the SCK, the strategy of SCK has evolved during these last years, and since 2022, we have mostly three main pillars of activities, besides the other activities that we are doing, and our strategic development now are built on these three strategic pillars. The first one is related to climate change. The second one is the fight against cancer. And the last one is circular economy, where we will deeply focus our attention right now, especially with the two presentations that we will present to you. I will just give you a first sight on the climate change and fight against cancer for general information and also that you know better SCK CEN. So concerning the climate change, basically we are mostly working on two main projects that you have perhaps already heard about. The first one, SCK CEN is developing since a few years, first fast lead-cooled reactor, SMR, small modular reactor. So we received 100 million euros to start the concept of this SMR, and we are working together with Italian company Ansaldo and Romanian company also to develop the concept and though afterwards to build it on the site of SCK and to let this operate by the year 2030. 2035. A second important project also that we are developing at SCK CEN is the MIRA accelerator-driven research reactor, which is also developed for the climate change. And for the MIRA project, there are basically three goals. The first one is to have a device capable to perform tests on nuclear materials for the nuclear reactors. The next objective is to develop radionuclides for medicine. And the third one is also to reduce the radiotoxicity of the radioactive waste. And by doing this, especially for the high-level waste, by optimizing the solution for the management of highly activated waste and to optimize the geological disposal. So that's for the climate change. The MIRA project has a first budget of 500 million euros, and the first phase is now starting. So this is the linear accelerator that you can see here on the screen. Concerning the fight against cancer, perhaps you know that in Belgium we have the BR2, so the Belgian reactor 2, which is producing around 25% of the radioisotopes used in medicine. And these radioisotopes are worldwide used. What we are doing now at the SCK CEN is also to develop other types of radionuclides, 4 types basically of radionuclides, to address 3 different types of cancers, and that's really our second strategic pillar. Concerning the last strategic pillar that we will talk about today at the SCK CEN, we are integrating the circular economy in the end-of-life cycle of nuclear installation. So what you can see here on the screen, which is divided in 2 parts, we are mainly focusing on 2 aspects. The first aspect is to minimize the radioactive waste and also optimize the process and the design of nuclear installation in order to reduce the quantity of radioactive waste. That's for the first part here above. And when we arrive to the minimization, there will still be a residual part of radioactive waste that has to be safely managed, and that's also what we are doing. So concerning the waste minimization and optimization, we are acting on different levels. The first level is the minimizing the radioactive waste production of new installations. So we are doing what we call minimizing by design. I've spoken about the SMR LFR, spoken about Minerva and Mira. So every time we produce and we make a concept of a new installation, we really think how to design it in order to reduce the radioactive waste during operation of the installation and also during the decommissioning of the installation. The second part where we are also acting is when we plan the end of life of our installation. So you have to know that SCK CEN is quite well known in dismantling of nuclear installation. We are dismantling our own installation, but also supporting the dismantling of nuclear power plants. So basically, what we are doing is strategic high-level schedule of the dismantling, but also provide consultancy services for characterization of waste and also development of waste stream in order to reduce again the radioactive waste quantity. We also foster as much as possible the reuse of material. And if we cannot reuse it, we foster the recycling of the material. And this is the objective of this today presentation. We will focus on the recycling of materials related to conditional release. Sven will speak about that in the coming minutes. And I will speak about the RECUMO project, which is focusing on recycling of a spent nuclear target. Then at the end of this process, there will, as I mentioned, remain a small fraction of radioactive waste, and we have to handle it in a safe way. So what we are doing at the SCK CEN is to develop new processes for the treatment and conditioning of radioactive waste. We are doing that by developing new binders, dealing with special waste forms. We work especially on liquid metal, for instance, as radioactive waste, and we also develop new characterization technique. Afterwards, we also investigate the long-term storage and the long-term behavior of the radioactive waste by taking into account the behavior of bitumen with time, but also the cement pathology developing with time, and also the behavior of fuel, and especially the fuel that has been used by SCK CEN the last decades. We are also developing together with the waste management organization on Rafnaris in Belgium the final disposal. So we are performing the safety calculation, the disposability analysis of the waste in this disposal. This disposal can be surface disposal or can be geological disposal. And last but not least, we are also working on the site remediation, including the circular economy, but trying to valorize the products that we get from the site remediation. We are working closely on the side of Umicore, but also on our own waste. So that's for the generic introduction of SCK CEN. Now I will go deeper into the project RECUMO. So RECUMO is, as mentioned on the slide, a solution for the residues from the production of radiopharmaceutical radioisotopes. RECUMO stands for recuperation and conversion of uranium from molybdenum 99 production. So basically, first of all, I will go into the context. Where does it come from? Why are we now speaking today about RECUMO? Why SCK is busy with this RECUMO? So basically, as mentioned earlier, you know now that the molybdenum 99 is a very key important nuclear medicine radioisotope that is used to perform diagnosis, also used to treat some cancer. And you have to know that in Belgium, we produce 25% of the worldwide production of these radioisotopes to treat per year about 7 million of patients. So basically, the main activities in Belgium, first of all, we make the irradiation at the SCK CEN of target, uranium target. This occurs in the Belgian reactor 2. So you have seen in the beginning, I've shown you a picture of this BR2. And then when these targets have been irradiated, they are transported to Fleurus in the south part of Belgium at IRE. IRE is the Institute for Radioelements, so a specific institute for the production of medical radioisotopes. And this target coming from SCK CEN are then chemically processed in order to extract the radionuclides for the medical isotopes. So mostly the molybdenum, which is a parent of the technetium, which is mainly used in the medical image and scanners. So that's for the context. If we want to go a little bit deeper into the process, you can see here on the slide, I will not go too much into the detail, but how this process is done. So as I mentioned, first of all, SCK received target, uranium target, which are manufacturers that can be high-enriched uranium. And in the future, we will go to low-enriched uranium in order to avoid proliferation of highly enriched material. Then this is irradiated into the BR2, and as mentioned before, transported to IRE, where there are a lot of chemical processes in order to obtain molybdenum 99, but also iodine and xenon at IRE location. And all of this process, at the end of the process, we get on one hand the valorizable radioisotopes that we want to use for medical purpose, but by this process we create also residues or byproducts that are at the end radioactive waste, and that's what we call the irradiated uranium residue. So basically, all the projects that we will discuss now today is to see what can we do with this residue. So the objective is not just to produce this radioactive waste and then to send it to IRE to the final disposal, but the objective really of SCK CEN together with IRE is to integrate the circular economy and to have a sustainable process for the production of medical radioisotopes. So to do that, it was decided to create between SCK and IRE a public-public partnership in order to deal with these residues coming from this process. The aim of these partnerships, there are different aims, different objectives. The first one is to condition the final residues into the waste form which is acceptable by the waste management organization. So meaning it meets the waste acceptance criteria from IRE. Second objective was to provide a sustainable solution applicable to both the highly enriched uranium and the low-enriched uranium in the future, and to transform this residue into reusable raw material. So meaning that we are reusing and reinjecting this residue into this chain of production of radioisotope in order to valorize them into the future. So as mentioned, in addition to that, the objective is to downblend the high-enriched uranium to low-enriched uranium, and to recover this low-enriched uranium to re-inject it into the production of the radioisotope. And also an important part was also to valorize our own expertise at SCK CEN concerning the radiochemical expertise. So that's really the scope of RECUMO. The objective is to recycle the residues and to re-inject it and valorize them into the production of the next radioisotopes. So I will go a little bit more into the detail of the project. So on the screen, you can see the location of the new building. This is the black building, is a RECUMO building, which will be built on the site of SCK CEN in Mol, so in the north of Belgium, located not so far from Belgo process. And RECUMO is being constructed right now in what we call the radiochemistry site or SCK site. Here you have another picture of the building. So you have a width of around 40 meters, a length of 40 meters with a head above 15 meters. And that's the design that you can see. And right now, what we are doing is to construct the civil engineering part of the project. If I'm going to a little bit more into the detail of the process of RECUMO, and I will go into the different steps in the next slides. You have a first step, this is before the RECUMO project. So basically it covers the transport from the residues from IRE to or BR2 for storage. And then it will enter into the RECUMO site. And in the RECUMO site, and you will see afterwards, there are basically two main parts. A process which is done in hot cell because the activity of the residues with the fission products, with the uranium and the plutonium are so high that we have to use hot cell. And then the second part of the process is done in a glove box because level of activity is lower. So basically you have two main parts in the RECUMO process. And at the end of the process, you can transport it again to reuse this new target, to irradiate them again in the BR2 and to send it back to IRE. So we will go into these different steps. So the first step is a transport. So we are using a MW transport container. This transport container is filled with 15 canisters, and in each of these canisters you have 4 cans, and these are transported from IRE to our BR2 building and placed into overpacks, which are boron overpacks in order to avoid criticality. So that's the first step. It's transport and storage at the BR2. The next step, it will enter into the RECUMO building, and there will be a storage zone in the RECUMO. So it's a hot cell for storage, which will provide us a production inside RECUMO for 3 to 6 months of production to perform the recycling. In this storage, afterwards, we will enter into the real chemical part, and this chemical part is to take basically the spent target and to perform dissolution of the spent target, to make the destruction of the organic compound, and to proceed to a first down blending to go to an enrichment of 30%. Then there will be a high active feed preparation. This preparation is needed to prepare the liquid-liquid extraction. So the objective of the first extraction is to extract uranium, plutonium together from the other fission product. This is done in the hot cell. You can see that on the screen. The extraction itself is done into centrifugator. You can see here on the screen a picture of the centrifugator. And after the first separation done in the hot cell, a second separation is done in the glove box. So this is for the separation itself. It gives you a little bit more detail. I'm just insisting on this point here in the middle. What is important, this extraction is done into 2 major steps. The first step done in the hot cell is an extraction. On one side, you have the uranium plutonium, which is co-extracted using the TPB-based liquid-liquid extraction. And in the second step of the extraction made in the glove box, it's a purification or separation between the plutonium and the other fission product in order to get purified uranium. So in the glove box, at the end, you do a second down blending to arrive to an enrichment of around 20%. Then you have a precipitation and a calcination in order to get an oxide, an uranium oxide. And this uranium oxide is then packaged in order to perform a new and to produce a new uranium target to be reused in the production of radionuclides. At the end of the process, as I mentioned, we still have residues. So we had residues here. At the end, we can get new targets and can reuse them. But still, we have a few of residues, and what we have is high-level liquid waste that are still remaining after the process. And after having identified different type of processes, we've compared cementation, vitrification at different location. We decided to go for vitrification on the site of SCK CEN. And to give you an idea, the total 25 years of production in RECUMO will result in one container like the CSDV container. So this is the same container that you get with the vitrified waste same time coming from La Hague after vitrification. So after the 25 years of production, we get 180 liters of radioactive waste that can be then transported to Belgo process for storage and then to a final disposal site that is still to be decided in Belgium. So RECUMO, basically, if we speak about the short-term planning, there's been a royal decree granting the license in 2022. The objective is to start the hot commissioning in 26 and start the treatment of all the residues in 26. So when I speak about all the residues, it's all the residues coming from the decades of production on the site of IRE for the radioisotopes. It gives you here a little bit more detail about the different steps. So we have first the interim storage at the site of SCK, the design of the chemical treatment, the hot cells and the envelopes, development of infrastructure, the procurement and engineering, which is still ongoing. And so the objective, as I mentioned before, is to start hot commissioning in 26. Start first with the high-enriched uranium residue, and then to continue with the low-enriched residue, which is the final objective for non-proliferation purpose. So what is the conclusion at the end? Right now, where are we? So as I mentioned, we've built the civil engineering part. We've performed and we have developed the chemical process and the engineering of the chemical process and has been now thoroughly tested and stabilized. We get the license for the RECUMO and we have granted also the general contractor to construct the RECUMO. So I arrive at the end of the first presentation of the RECUMO. I give the word now to my colleague Sven. Sven, if you can take perhaps or share your own screen with the presentation. We'll stop sharing.
Yes, thanks. So thanks, DJ, for your interesting talk and sharing your insights with us in this field. I would like to say that if there are questions about this presentation, please put those in the chat and we can answer them after the second presentation of Sven. So now we will have our second speaker of today, Sven Boden. He's a nuclear engineer with over 30 years of experience at the Belgian Nuclear Research Center, SCK CEN. He has been involved in various decommissioning projects from start to finish. Currently, he leads the Characterization and Clearance Activities Unit and plays a central role in advancing sustainable nuclear waste management through specific clearance practices in Belgium and Europe. Sven will tell us more about the role of specific clearance in sustainable nuclear waste management in Belgium. So please, Sven, the floor is yours.
Thank you for the introduction, Veronique, and very good afternoon to everybody. So this second part, the second presentation, it will consist of four different aspects. So first of all, I will give you a very brief introduction on the Belgian regulatory framework. Then I will move on to, in terms of specific clearance, to show some assisting tools and systems that are necessary for the implementation. I will then go on with some implementation, some examples, and I will conclude this part with some challenges and outlook for the future. So first of all, the regulatory framework, as well in worldwide, most projects, let's say in nuclear decommissioning and waste management, use the IEA GRS Part 3 for unconditional clearance, and At the European level, there has been also some harmonization in 2013 with the implementation of the Basic Safety Standards Directive. So for unconditional clearance, we use basically in Europe all the same clearance levels for all individual nuclides. But at the end, the basic, let's say, requirement for applying a clearance and reuse and recycling of materials is the 10 microsieverts criterion for every member of the public. So it should be in the order or less in a year, the dose uptake for every member of the public. So let's say 20 years ago, when we were dealing with rat waste and with the decommissioning waste, in many cases, what was in practice applied was a kind of zero tolerance. So whenever some traces of radioactivity, artificial radioactivity would be present, it would mean automatically, let's say, rat waste. But let's say the last decades, it has changed, and also the mindset has changed, because of course at the global level, at the conventional waste management level, there is also the European Waste Framework Directive saying, okay, we have to try to prevent waste, and then first look to reuse, then recycling, recovery, before we can look into disposal. And the nuclear sector is not different from, let's say, the general waste management that has to be applied. And yeah, lately we have revision and this IEA document, GSTS 18, which is also taking that on board. If we look to the Belgian level, in Belgium, in our legislation, there is also mentioned the minimization principle, so Article 33.1, basically saying that we have to try to minimize the radioactive waste production, and that should be achieved through appropriate design measures and good practices in operation and decommissioning. And of course, we have to follow, well, this upside down triangle you see above. So we have to first try to avoid waste, and then reuse and recycle the materials before considering it as radioactive waste. Okay, so if we look into detail, like it is, I think, implemented in many countries, there is what we call at the left-hand side for materials that can be unconditionally cleared. That is what we call unconditional, or used to call unconditional clearance, and to define this limit values, well, some, let's say, in international scenarios have been set that has been on the conservative side, let's say, and then a dose impact study is being done, rounding procedure to arrive at nuclide specific clearance levels. And then when you have a mixture of radionuclides, then you have to apply some formula. And then you have, let's say, the operational clearance levels, and then of course in practice you're not with waste. It's not like grams or low amounts of materials. In many cases, we are talking about several tons, hundreds of tons, thousands of tons. So there is also an averaging that can be applied. On the other hand, there is also the conditional clearance, or today it's called the specific clearance according to the IEA, and here the concept is that we have to prove that the effective dose that can be incurred by a person should be below also the 10 microsieverts per year. But here, let's say we know the process that the material is going to follow, so we can apply very specific scenarios to derive the individual alarm levels for the individual nuclides. In Belgium, because this kind of concept, it is used in, let's say, already other European countries as well, but the actual implementation can be different. So in Belgium, for unconditional clearance, so we have for mass-specific clearance levels, the basic safety standards directive that is being implemented. So those values, and we also use values that are surface area per surface area. And on the other hand, the specific clearance process, that is really a case-by-case process. So we have to, let's say, do a specific dose impact study for a specific case to get a license to use that. And on the right-hand side of the slide, you see the 7 requirements that need to be fulfilled. So of course, well, you need to have a good history on the material. You have to do a dose impact study for the various scenarios. You have to see that maybe with decay storage, you can also, let's say, apply the clearance, and also reuse gets priority over recycling and over disposal. You need to have full traceability, of course, and your measurement procedures and techniques should be fully approved in advance. And of course, the final destination of the material should be well defined. In Belgium, if you have a limited amounts of material that would follow this process, so limited amounts of material, smaller than 1 ton a year, then you don't have to perform a dose impact study when the activity concentration levels are below the exemption levels. So let's move on to the assets that we can use. So the traceability, of course, there, we have always full traceability of the waste streams from beginning to the very end, and this kind of databases with getting all and let's say registering all data, they are being renewed today. Another parameter is, of course, the source term determination, and there, of course, sometimes it's based on full mass and full volume measurements, but in some cases also taking samples and relying on the samples and doing further data analysis to get a result on the full population, let's say. Also, other type of measurements that are being performed can be in situ, but also ex situ measurements on large volumes. If you see on the bottom picture, where today we apply more and more, let's say, big measurements on volumes of 1 cubic meter or 1 ton inside an equipment with big plastic scintillators, and of course also destructive and non-destructive analysis need to be applied to get a full picture of the source term. Also today, because like I said, sometimes when we're dealing with large volumes, we rely on sampling and also doing some more advanced calculations to have a spatial categorization of the materials. So, and here we see an example. I will come back to that later on the biological shield of the BR3, where we applied a source term determination from the very start, so in the very upstream of the process. So that means that we did already the categorization before even doing any segregation, and defined where to actually segregate between the material that could be later on unconditionally cleared and the material that could be that was, let's say, dedicated for specific clearance. And that kind of model was approved before actually starting with the segregation. Other assets is, of course, the dose impact calculations. So the typical scenarios we usually have to perform is looking, of course, at all the materials that are being created during, especially in the recycling. It could produce primary, but also secondary materials, tertiary materials, and those have to be all embedded into this dose impact study. The exposure pathways are inhalation, ingestion, and external exposure. And of course, we are looking always to the workers that are directly involved, as well on site, but also during like transport, recycling, handling, and final use of the material. And we also, of course, look to the public on the short term and on the long term, so effects on food chain and water management. So for this, so this kind of studies, and if you have to do that case by case, we developed a tool, a specific tool to do this kind of dose impact studies. The tool is called RIAT, Radiological Impact Assessment Demonstration. And so for every case, we can do this kind of calculations with some specific calculation tools behind. And harmonize, let's say, the way how we perform the dose impact. Other aspects that are sometimes important is, and where some parameters that are being used are sometimes not 100% known. So sometimes some testing has to be done, and specifically for KD value determination. In specific cases, so we also have the means to perform some laboratory tests to define KD values if critical, if needed. Then the step to the implementation. So as you can see here on this slide, the first time that the specific clearance was initiated was in 2014, and that was the first case. So that took quite some time to get a license with some, let's say, Q&A with authorities, a lot of discussions on how to do things and to understand each other very well. So it took us about 3 years to get the license, and then a few months later we could let's say transport the material. In this case, it was going to a conventional disposal site. If we look at the current implementation of this specific clearance, so I think nearly every nuclear site licensee in Belgium is currently applying this. So we as SCK CEN, but as well the other organizations you see mentioned here already applied the specific clearance, and also today still with the case by case ad hoc process. So that means from the moment, let's say, the cases that have been already implemented, there is a rather limited variety of materials, let's say. And the harmonization there is, I think, today also a little bit limited, because it's like case by case and everybody uses sometimes different tools to do the dose impact studies. And of course, there are quite some high, let's say, still turnaround times. However, of course, not 3 years anymore to get the license. So today, it's about, let's say, 3 to 6 months to get a license. But still today, the disposal option that is being used is the conventional disposal option, and there are already a few cases of recycling, but that still needs to be further developed and implemented. An example, I think, of the largest amount of material that have been specifically cleared is the biological shield of the Belgian reactor number 3, which was a pressurized water reactor, where about 1,000 tons of materials has been transported to a conventional landfill site for hazardous materials. So 1,000 tons of in total 2,200 tons of biological shield. So the remaining part is today still standing, but when the building will be demolished, it can be recycled because it's unconditionally cleared. So this mindset change to use also the recycling and so on. As we see in the Belgian regulation, there is mentioned also the ALARA principle for the sustainability. So let's say if we use the ALARA principle for the safety and radiation protection, and there we use the limit, of course, of the 10 microsieverts per year criterion, but below that we will not further, let's say, optimize, because this could not be aligned with also having the ALARA principle for sustainability and for optimizing the amount of material that can be cleared and recycled. So that there we have to find the right balance. The challenges that are still existing is, of course, it's a quite complex process. So with the tool that is currently nearly to be implemented, we will try to harmonize the dose impact calculation approach and to also apply it for huge volumes and also for more waste streams. And also to go more towards recycling. But in every case, we need to know the process that is being followed in a very detailed way. And in some cases, it might be even also needed to do testing for defining KD values. In any case, quite a lot of parameters are here involved, and sometimes today they are on the conservative side. Also, another big challenge is, of course, and especially in terms of decommissioning, and when you still have to produce the material, you need a very long-term strategy, and there are quite some stakeholders involved. And if we are now making plans for other decommissioning projects where the materials, we think they will be only produced in 10 years' time, and we have to make agreements with organizations that will do the conventional recycling, it's not so easy to do that. Because also, there is the duration of those kind of decommissioning projects and also the licensing process. So, and to have their long-term commitments and stability, it's a real challenge. And last but not least, of course, there is really, I think, also a need to, in terms of sustainability, to go more from the landfill disposal to the recycling. And there also it comes a little bit together with also those impact studies. In some countries for, let's say, landfill disposal, there are fixed limits. We always have to approach it in Belgium case by case. and to find there a good balance, because with the case-by-case approach, you could be able to recycle much more than with the generic approach. But yeah, it's of course more costly and more time consuming. To conclude, I would say that in Belgium, applying specific clearance, the regulatory framework is existing. It's being implemented today, but it's not optimized towards recycling yet. And yeah, the challenges are mainly related to the complexity and the long-term strategy. So I thank you for your attention, and I think I give back the words to Veronique.
Yes, thanks, Sven, for your interesting presentation. We've learned a lot from your knowledge and insights. I see that we already have one question in the chat. So if there are more questions, please put your question in the chat and I will ask Sven and DJ to answer them. So the first question is, what specific technologies is Belgium investing in for sustainable waste management?
I think today, let's say, we are looking basically at the two big type of materials that are being produced and that could be recycled is the metals, of course. That's one part of the materials. And there we have today at SCK we have the smelt project where we try to optimize this way of let's say recycling more metals than we can do today. And then but there is not, let's say that there is not a big start yet, but also towards building materials. I think there, like concrete and so on, we will look into that as well. I don't know if Didier wants to add something there.
Yeah, as you mentioned, Sven, indeed, the smelt project is an important project into the decontamination and the treatment of metal parts coming from the reactor pressure vessel and the internals. That's the first project where we are working on to perform first research and development, and also to improve the general melting process in order to separate radionuclides from the metal and to be able to recycle the metals. So besides this project, we are also more and more developing, as I told you in the introduction, the site remediation. We are also looking to valorize byproducts from chemical industries. The objective is not only to make site remediation, but also to make a valorization of the products on site in order to valorize them for the future in the economical chain. And also in order to continue to reduce the waste and the radioactive waste, we are investing more and more also in a better characterization of the waste to reduce the uncertainty also, and so to release more easily the waste from the radioactive waste management, and so to be outside of the nuclear regulatory control. We also develop new binders in order to get a better inclusion of the waste into the drums. So all these activities that are now running, I've spoken about also RECUMO, which is a typical technology that we are using, like a first of a kind. I think it's one of the questions that is coming, is also technology that we are developing in Belgium, really to push into the sustainable management of radioactive waste, but also to foster the circular economy into the nuclear field.
All right, thank you. I hope this will have answered the question about this specific technologies. And you, DJ, you said it already, there is a question about the estimated budget for the RECUMO project. Can you tell something about that?
Yeah, so as I mentioned, it was decided in around 2017 to start a public-public partnership with the support of Belgian state. And so now we have an envelope for the RECUMO project, which is estimated around 250 million, 300 million euro. So that's a global amount for the construction of the installation.
All right, thanks. And we have another question that has 3 parts actually, but I will start with the first one. Regarding the recycling of the LEU for molybdenum-99 target production, has it been done already?
So I will start by answering that. So what has been done for the moment, basically, at SCK CEN is first to develop the process years ago to make the separation. But it's true that in Europe, it's like a first of a kind that we are now developing in our institution together with IRE. So that's answer, I think, the question. And part of the process is also related to the Purex process that is also used for the vitrification of spent fuel. So not for molybdenum itself, but in the context of separation of radionuclides that's already existing. But concerning the molybdenum itself, it's indeed the first of a kind that we are now developing in Belgium.
So
and now also already contact with other countries that are also interested in this in this technology. Yeah.
All right. So I think you answered all 3 questions in this first part already. I see other questions coming up. Why do you use centrifugal extraction instead of mixer settlers or other method for separating U and PU?
Yeah. So basically, yeah, that's I'm not the specialist inside this field. I just take the question. What I can answer to you is, as I mentioned, we compare different technologies before starting RECUMO. So as I mentioned, RECUMO started a few years ago, but it's based on the technology that has been developed at SCK CEN since now decades. And so different technology were used at that time, and it was indeed selected to go to a centrifugal extraction. But now to tell you what is the reason for, I will have to go back into the more technical experts working on this field. But it's indeed a choice, a technical and economical choice that has been done and implemented in RECUMO, because we would like to use something which was proven to be stable, as I mentioned in the presentation, and we could also run it already at the SCK CEN before.
All right, thanks. I think the next question is for Sven. Is there a limit for the amount of material that can be cleared using the specific clearance procedure?
Yeah, of course, a license is always connected to a certain source term and also to a certain mass per year that can be recycled or removed. And when let's say that's a kind of balance, when you would increase the mass, it would have an effect on the dose impact. So it could lead to lower activity concentration clearance levels, and vice versa. If you let's say reduce the amount of material, it might also have an effect on increasing the activity concentration levels you could recycle.
All right, thanks for clarifying that one. We have another question coming up. When it comes to radioactive waste supply chain, do you encounter challenges in ensuring compliance given the complexity of the regulatory landscape?
I don't know if I would I interpret the question correctly, but if it's about ensuring compliance towards masses volumes, that is in principle not a problem, I think, but it's more towards the radiological aspects, the radiological parts with activity concentration levels and so on. I think for that there is already quite some experience and implementation in the unconditional clearance as well. So there is in principle not a big challenge, I would say. But for the supply chain, I I don't know exactly if I interpreted it well and if that's an answer to your question. Otherwise, could you maybe rephrase a little bit?
All right, we'll see if it happens, and if not, I have another question in the meantime. Can you share lessons learned from the BR3 biological shield disposal project, and how can these experiences improve future decommissioning practices?
Of course, going through such a process, there are always quite a lot of lessons learned. I think, the most important one is to let's say we applied clearance and sending the material to conventional disposal site, but we think in the future and in view of really implementing sustainable waste management, we should go more to recycling. So this is something that that is for future projects that we certainly will look at. If we look to let's say, what Didier mentioned, the design, if we look at the PWR reactor, the reactors today, they don't have any neutron shield tank. In the BR3 reactor, we had this kind of neutron shield tank, and we saw that the activation levels of the concrete were much lower than in a commercial power plant. So that kind of designs could be really good to reduce the waste in the future, because the activation levels are much lower, and also with some kind of decay. So I think we only started the segregation of the biological shield more than 25 years after shutdown, so with some decay. And at that moment, also the activation of the reinforcement was about, let's say, lower than for the concrete, so that there was no need to separate both. And also for the biological shield, let's say this type of upstream characterization where you produce a model and where you have like a digital twin that is approved and used for the segregation, that really is helping you quite a lot in the process during the segregation, because we see today many projects in Europe where the segregation process is really, from planning point of view, a very difficult thing, and with a lot of delays and so on, and a lot of extra costs. And if you have everything already approved in advance, you win quite a lot of time and money in the execution.
All right. Thanks for clarifying that one. I think we can have one last question. Looking at the time, it's almost 2. What criteria are used to determine whether a material qualifies for specific clearance, and how are these criteria validated?
Well, I think we have here a combination of 3 aspects basically. First of all, there is the sustainability. So we need to have a recycling process existing, and if it's not, then it would be difficult, or it can be done, of course, for let's say in the RECUMO project, it has been done to design a specific process for having the recycling. But for many materials, it would be interesting if there is already something existing there. And typical for typical material, which is also chemical hazardous waste, for instance, sometimes already processes are existing, and that can be really interesting to be used. A second aspect is the safety. the safety aspects, of course. So that's the very important criterion is the dose impact. We should follow, of course, the legislation, and we should be below the 10 microsieverts. Well, in principle, the international level is in the order of 10 microsieverts per year, but in practice, what we can implement in Belgium is we have to prove that we are below the 10 microsieverts per year criterion. An aspect there in the safety is also always in the process of the recycling, there is usually some dilution being made. But it's part of the process, so it's not, let's say, intentional dilution here. But to have the balance between dilution and concentration, that's from safety point of view and ethical point of view, not always that easy, and it's, I think, also important criterion. And then last but not least, there is of course also the cost. For metals, usually optimized recycling, there is also an incentive in the costs. For other materials, it might not always be the case, and that can be a very important criterion to be used.
All right, thank you so much, Sven, for answering this last question of today's webinar. Looking at the time, it's the time to close the webinar right now. I would like to thank DJ and Sven for their presentation today and for sharing your knowledge with us. And also thanks to everyone who attended this webinar. I hope you all learned a lot today about the challenges, but especially the possibilities for a circular economy in nuclear. It was really nice to have so many of you here today, and have a great day.
Thank you. Thank you all. Have a good afternoon. Bye-bye.
Thank you. Bye-bye. Thank you.
Bye.